Okay, so this afternoon we are privileged to have Dr. Rodwell Kufakunesu from the Department of Mathematics and Applied Mathematics, University of Pretoria in South Africa. He's going to speak to us on the representation of backward stochastic differential equation based dynamic risk measures and dynamic capital allocations. So I think that your time is now. You are most welcome.
Thank you, Professor, for giving me this opportunity. We got the topic here. I'm just going to share with you what we've just done recently with some of my collaborators who I think who has joined in is Lesedi Mabisela is here with us, but I'm not sure. Okay, so I'm just going to give some preliminaries of the tools which we used and then talk about the representation of the dynamic risk capital allocation, examples and conclusion. And right, so let us start. Why the topic is quite long, but of importance is the capital allocation. Capital allocation is very, very important in the enterprise risk management of organizations such as financial institutions and also insurance organizations. So the risk framework induces the need for capital allocations in various sectors. So this is the type of modeling where we are dealing with compliance, that these capital allocations, some of them are mandatorily advisory or proprietary. So it means you can be forced to allocate a certain amount of money to hedge against some risk. So to mind, for instance, if you look at the mandatory, if you have in the banking sector and in the insurance sector. So in the banking sector, we've got a Basel range of where I said, for instance, of Basel 2, but in some advanced economies, they've gone as far as Basel 4 right now. And insurance, we've got an equivalent, which is a creature of the European Union. Strictly speaking, they are implementing it Solvency 2, which are also a set of regulations equivalent to the financial sector, but this time in the insurance sector. So Basel II, for instance, is based on 3 pillars: minimum capital requirements. This is crucial. Minimal capital requirements, supervisory and review process, and market discipline. Solvency II, like Basel II, is designed around 3 pillars as well. For instance, the quantitative requirements, qualitative, and disclosure. In all this, risk measurement that lead to capital allocation is primordial. So that's why it is important to have a sort of a risk representation for these measures. So capital allocation is an essential application of risk measures. For instance, if one is interested in decomposing an overall portfolio or risk capital into some components, which are sub-portfolios. Okay, let's proceed. The reference of the talk is based on these 3 papers, mainly written by Lesedi. So we did a practical example of quantification of risk at a time when one of the banks in South Africa was going under. Actually, it was saved by other banks, the African bank, and then it did some valuation there and saw some pictures. So it's an interesting look at this one. And mainly my talk is going to be based on this one, which is, okay. So the dynamic risk, this has been studied already by various researchers, the connection between BSD and dynamic risk measures. And in our representation, we are going to show the converse risk and coherent risk measures on how we would have applied our results. Basically, this is the structure of our presentation. So let us start with the preliminaries. So what we normally what we have here is the filtered probability space, which is the standard Brownian motion. Okay, this is for the diffusion, and then we also incorporate the one which can capture jumps, the independent compensated Poisson random measure, which will be given like this, and then the filtered probability space will be like this. Then we can actually augment the two like that. Okay, here we can just put the space. It's not a product sum on this one. Okay, and then because we are going to work with the BSDEs, they need some housing structure. So where they live in some LP spaces, and we also have this space of Cadillac processes with this condition, and also some predictable process, which is in H2, and with this condition. We also have the predictable process for the jumps. This is for the diffusion. So for the jump process, we'll have that. And basically that's what we need. We shall need also the Gisanov transform, which is a very important theorem in mathematics of finance, where we have the relationship between the objective probability measure and the risk neutral measure. But it is quite simple when you see it in the diffusion framework. But when you go to jump diffusion, we have it represented in this manner, where it continues to be related this way. At times it appears as let's say dq dp like this, with some density process. This is the density process, and these are the way you would change the noises, the Poisson noise and the diffusion noise to involve a risk neutral probability. We shall need that. Also, we shall need the bounded mean oscillator for the jump diffusion. This is to control our jumps, and also some conditions. Kazamaki criterion is quite important here. Also, it will give us the condition for uniform integrability of our density process here. Now, as you shall see, we are going to talk of gradient allocation of risk. We are also going to take advantage of using the Maliavian derivatives. This comes under Maliavian calculus, which is a very important tool of unbounded operators, which are closable, and which will facilitate you to be able to differentiate things which cannot be classically differentiated. So Maliavian calculus here will be considered as a directional derivative in some special space D, which is a Banach space of random variables with this norm. And we got Clark-O'Connor, which gave us an ITO representation theorem, which you are seeing here. But Clark-O'Connor and Carruthers gave us as far as this, that's the diffusion. And then in Oskendal, also we can see that he extended this to include the jump. So this is none other than an ITO representation theorem, which to some extent will give us explicitly these integrands, and these integrands here can be interpreted as the Greeks when you are doing some derivatives. Okay, there is some example here. We are looking at the chain rule. So if you visit this reference here by Oskendal and Frank Prox, and also if you have in the audience, I'm not sure whether Olivier Pamin and Farai Mhlanga are here. They are the specialists I consider to have studied this. Maliaven, also sure Matarambra did it, and you can use their thesis. They're available online. Their dissertation at masters and PhD alike. So you can revisit these properties. So this property is a way of handling Maliaven calculus. You can do like this is what you wanna apply your Maliaven calculus, and then times the first derivative, sort of the argument here. And also when you're involving jumps, you can actually do this. So you can see, for an instance, if you wanna deal with an exponential, applying your Maliaven derivative. So it will be the first, so here it's like you're now differentiating the noise, the Brownian noise, which we say in the classical sense is no differentiable, but here you would see an indicator function coming out, and also applying such a property here, you will have to see that if you are differentiating something like a jump term like this, which contains the Poisson compound Poisson process, it will come out this way. So it will be f plus, like what is being indicated, f plus the first derivative here minus the function which appears in the integrand minus k, and then that's the result. So those are some of the tools we need. Now I come to the risk measures. We are going to consider X kappa, the space of financial positions that are defined in a probability space. So normally we can consider P to be included from 1 into infinity, but yeah, and then consider LP like this, LP with this argument of our measure space. So also, like what I've alluded to, we'll then put a topology for us to have this measure space to be Maliaven differentiable. And normally there's a, we normally work in L2 LP because of L2 is the best because of the joule of L2 is L2. So that will be the best. So here we can therefore say this mapping is a subset of LP, okay, throwing values to R like this. And then we have these properties of monotonicity. If you check what monotonicity will will mean we have a position here, y, which is less than the position of x. But if you are now looking at the measures, we can say if you've got a bigger portfolio, it has less risk than a smaller portfolio. And then we'll have also this condition here, the translation invariant given by some m here added and then subtracted. What does this mean? It means if you are to add a constant like m here to x, then we can reduce the risk accordingly. That's why I got a minus here. And subadditive property, which is also a very important one, which then throws out the value at risk, because value at risk, which we normally calculate the amount of money we are likely to lose, the maximum amount we are likely to lose, then value at risk will not satisfy this condition. But if you then use some averaging of it and consider something like tail val, then you see that it becomes a subadditive. What does this mean? It means our representation do not contain a value at risk as we know it. And then we got positive homogeneity, and also we got convexity, which has got the same interpretation as diversification reduces risk here. So you know you got this the risk of portfolio X and the risk of portfolio Y. Their individual risk is greater than if you consider the portfolio as a portfolio. That's the common notion of risk here. And a coherent risk measures then will satisfy positive homogeneity, monotonicity, translation invariant, subadditive, and convex risk measure satisfies the convexity property, right? So we then come on to capital allocation. So we've got X1, X2, up to Xn. These will be like departments of portfolio. If it is a bank, we'll be considering some credit risk department, some market risk department, some operations. All these are sort of mandatory sections where capital has to be allocated. If it is a non-financial sector, you can consider as your diversified portfolio. If you got a big organization in various countries, you can also consider these sub-portfolios. Then you got your X, which will be the sub-portfolios, the subsections, like that. So the capital allocation problem is to allocate the overall risk here, the overall risk, ROX, of the portfolio and the individual portfolio. And then we will require that the sum of our risk given the total will be equivalent to the total risk. So we then use, there are many ways of doing this, but in our case, we're going to use the full allocation property, since the overall risk is fully allocated to individual sub-portfolios in the portfolio. And also, what we choose among these will be this case here, which gives us the vertex, which is directional derivative vertex differentiable at x, and then the gradient allocation. So this is also not known as Euler's method, or I think the name I'll give is here at the bottom, Oman Shapley. So what is it saying here? You are doing your gradient allocation in the direction of the portfolio or sub-portfolio XI. And then you evaluate at 0. It can also be looked at this. So you see this beta here. This beta is coming from the portfolio weight. The weights you would give to each subsection, like beta 1, beta 2, beta 3, and so on. So that's why you will have to sum your gradients of the risk in the direction of XI this way. So if the risk measure rho is positive homogeneous, then Oman allocation reduces the gradient allocation principle to it. You can refer this statement in D note. For Oman Shapley, we do not require the risk measure to be positively homogeneous and for property. However, the gradient allocation does need the risk measure to be positive homogeneous. Okay, that's just a comment here. Now, I've already alluded to, I still remember there was a very important conference which was held by Professor Oskendal before he retired in 2017. He gave us lectures on stochastic control, where he talked a lot about this connection here. This connection has been studied by Professor Shoma Taramvura in his PhD thesis, and there's a popular paper. But in that paper, or in his thesis, he did with HJBI instead of backward stochastic differential equations as such. So you can have a look. So he also worked with convex risk relations and also the recurrence type of relations when we are studying risk. So there are many references to this. I didn't put Oskendal, but I can also put Oskendal as notes, but I don't. Yeah, in his book on maximum principle, you can see that. So the G here is the generator. So mainly all these backward stochastic differential equations, they've got this generator, the diffusion term, and the jump term. And this is the terminal condition, right? The terminal condition. This is how it differs with the forward type of stochastic differentiation, or the classical, the normal one. All right. So because we have connected omega, and here we can actually fix it so that you can write it this way. And well, it's still featured, but you can remove it. So what do we call the solution of this backward stochastic differential equation? It is a triple. It is a couple. All these three parameters, y or process y, z, gamma, they adjust themselves in order to make the solution adaptable. The solution is adaptable and predictable. And this is where our connection is going to come from, the connection between this terminal condition and our measure, our risk measure. But of course, like what I alluded to in my earlier picture, that we shall need the differentiability of the solution of the backward stochastic differential equation. We then have to talk of these assumptions. So we then say the terminal condition is Ft measurable. The generator follows this integrability condition. You see the x, y, is it the y Z, Y, Z, epsilon. They start as 0, these ones, for every process YZ in this space, product space. There existed 2 constants, epsilon and I'm forgetting now the nu, and positive F progressively measurable LT, so that we got to these conditions. And yes, this condition will be written here, this one will be written here. And then also we got this growth, which has to be fulfilled. And yeah, and also this process here. And then the above assumptions can be found in Fuji and Takahashi 2018. They prove the existence of a unique bounded solution of a backward stochastic differential equation under 11. So in the article, if you go into the article, you'd see more detail. And here we are. I'm now asking you now to see this connection between the solution of the backward stochastic differential equation and our risk measure. This epsilon here came from the terminal condition. Then rho is monotone time constant dynamic risk measures. So we consider G to be sublinear and convex. And you'll see that they are sublinear and convex in Z. And we do not have in our solution the parameter, the process is Z. So Y is the first component of the solution, will be the first component of the solution. So Quinn and Solem, they proved that Z is not involved in connection to dynamic risk measures. So the differentiability result we captured here has been studied by Fuji and Takahashi in a separate platform, but they considered a quadratic, but on top of that, exponential generator, which they considered in this case. So the generator will be of this form. So you see the component of epsilon, which is the jump component, is also involved there, and some conditions have been put. So here we continue with the differentiability. Now, we are also going to consider it using the Malevin differentiability. For your information, there's downloadable lectures on the internet by Peter Imkela, did a fantastic job on the diffusion using Malevin calculus to show existence and uniqueness of backward stochastic differential equations. So it's the starting point before you can involve jumps. And here you see we're gonna differentiate the generator in a Malevin calculus way, and also involving the jumps. So this suited our application, our results, because we needed that, and also the condition being implemented there. So at the end of the day, we arrive at this there exists a unique solution which can be differentiable, which is differentiable like this. And our process will then be like this. So this can be constant, but it's also stochastic in some sense. And yeah, this is the jump one, and this is when you are using the diffusion one. using Malavian. They need to be done separately, actually. So we then here, one of our contribution we made was to extend the definition of gradient allocation, not using the classical directional derivative, but using the Malavian type. So what will happen is that this D will represent the Malavian derivative where it is needed. Elsewhere, we can use the classical directional derivative. So we combine the directional derivative with the Malavian. It is an abstract concept, really, because in practice, we're not sure what it really means, because the directional derivative of the Malavian is actually a sum of some iterated functions, HT. And we don't know in this extended version what it actually entails, whether it really exists in practice. But theoretically, yes, we managed to do something about it. Then I'll skip this part is part of the discussion of the differentiability of our solution of the backward stochastic differential equation. And now this is sort of our main result, which is well done in the article, in the paper. So the D will be a generalization now. The D is the Malavian gradient, where you will see that the generator, we are using delta here, but it's also the same using D, partial derivative with respect to these components here. So what is new is that the density of our measure change, the where these partial derivatives. So they are sort of in a wicked mode, and this is rhyming with what we call the entropic type of risk measure. So this is the main result, which then say the dynamic gradient allocation can be represented by this in its abstract format. So we shall see how to exemplify this result. But there's a sketch here of the proof. So what you notice that these are BMOs. That's where we needed it to control them. They are BM. Then the stochastic integral shown earlier on in 22 are said to be BMO martingales, and the stochastic exponential is a true martingale, a result found in Molais 2009. And from Dinuno et al. And others, theorem 1221, a new equivalent probability measure, the Q is defined by equation 22. So the change of measure, where in the classical sense we would see that this will represent sort of a market price of risk in some sense, but it is now wearing a partial derivative like this. So this G, remember, is quadratic as well. So if we are to define a function like this, then from the martingale representation theorem, which I've shown you earlier on, we can actually do some comparison of the BSD and the gradient allocation. And what do we get? This is what we'll get. And this is how our result, which I've shown you, is achieved, and where our measure transform will be given this way. And there's a corollary to this result, which then say let our terminal process be in L2, Suppose L is convex in Z and V, then we can belong to a class of BMO. Beta, remember beta comes from the portfolio weights between 0 and 1. Then this is what we get are the controls of backward stochastic differential equations. And also the terminal condition will be written like this. Then the corresponding quadratic exponential BSDE-based dynamic risk measure can be represented this way. So this will come here, and our M is defined by that. And yeah, and also there is another corollary which comes from there that almost similar in measures. Then the backward stochastic differential with coherent risk. This was referring to it was referring to dynamic convex risk, and this one is referring to dynamic coherent risk. And what we with its corresponding change of measure. This corresponding change of measure, as you can see, has been actually demonstrated how you get this natural log from the geometric jump diffusion in the reference by Oskendal, which I've alluded earlier on. So what we then do is suppose just in case to apply our results, suppose we are to consider this entropic risk measure. This family of entropic risk measure is a family of measures which I've alluded to earlier on. Normally, they let's say they are coming from this sort of family where this is a risk neutral measure, supremum of the expectation of that minus that. So if you then this is also a convex function, and it's termed the penalty function. So at times, if it is not there, if it is 0, then we sort of have some family of this nature. But yeah, this is the example we are going to apply our results, and then we then put the right hand side as the BSDE as it were, and this is our risk measure with all these jump diffusion terms put like this. Also with the help of the work by Caro and others in 2016. So the structure of our generator is like this. Note that the generator is given and the partial derivative. We don't have any problem here. The partial derivative will be gamma z, and that of the jump component will come to be of this nature. And suppose the classical smooth function, this belonging to D, then there exists, and this norm exists and is finite. And if we define our function e to the power minus gamma epsilon, then the boundedness of this, because it lives in a compact space, and any beta, we have this is a Malevin differentiable. So we take the conditional expectation and apply the generalized Clark-Oconee, which now involves the jumps. It looks like this. So look at the integrand we've alluded to earlier on. We define just by definition that so that we can summarize the writing here, where Z can be written like this, and you can see the malevolent derivative coming up. This is for the diffusion, and this one for the jump. Both are predictable control processes for the entropic measure defined by the Baker stochastic differential equation. Where am I now? Here. All right, so at the end, we can, I think I'm at the correct place. We can write it in this form. And then these are the transformations we need to do for the noises. And yeah, the phi, what is happening? Okay, the phi will be then given in this format. So at the end, we do the comparison and then we apply the gradient allocation of the entropic under the jump diffusion by 28, which is above. If epsilon is the portfolio and Ni sub-portfolio, then equation 28 describes the dynamic capital risk contribution of the sub-portfolio, which will be given like this. And yeah, so the representation of this dynamic entropic risk will be of this form. So that's how we applied our result to a non-entropic risk, which is which we have seen above here. And the other example 2, is when we described this static entropic coherent risk. And what we then discovered in this example is precisely what I see, the beta I can see here is the relationship between this gamma. So let me say gamma between 0 and 1. The gamma is also like representing the asset allocations, 0 or 1. So I can actually attest to the fact that the convex case. The convex case is the convex case is this one, and then the coherent case of example 2 will happen when gamma is equal to 1. Or I use the beta and gamma interchangeably in this talk. Right. So this is the representation of our static entropic coherent risk measure. So, like what I've alluded to, the paper is quite is highly technical, but I think I tried my best to explain the key features in the paper. In conclusion, we have just studied the capital allocation here of risk measures constructed the BSDE solution from the differentiability of the results of Baker stochastic differential equation of the jumps and the Mattinger representation property. We were able to provide a capital allocation representation of risk measures. Right. So it's for future. We then looked at the ergodic representation, asking other questions which are different from what we talked about in here. So basically, that's it. That's what I've planned to talk to you today. So I'll put again the reference there as there are the references. This is the reference of my talk. Okay, thank you